So this is the second part of the video on ergodicity, which I provide on Elias. Should have watched the first part, which yielded these notes, which we worked through, and you should ideally also have taken a look into this PDF, which I put on Elias, which provides measure theoretical basis of mathematical statistics, which I use here. Okay, so what I'm trying to do here is take a step further and illustrate this idea of linking time series stochastic processes to a probability space. And we saw this in the first video. We saw this idea of saying, okay, we take one draw from a sample space, omega, small omega, out of the big omega, the sample space, and that one draw gives us realizations of big T, in this example, big T random variables, which is essentially the realization of the stochastic process that we're interested in. Now let us try to make a little graphical illustrations of that idea. So what I'm going to take here as a time axis, this is T, and I'll have a process that is going to start at time 1 and that goes until big T. Okay, I like to put the borders here and here, and then I transfer this notion of a stochastic process, which is a collection of random variables, and these random variables are associated with this draw from the sample space omega. So I'm going to plot a realization of a stochastic process like this. Okay, and what this represents is a sequence. This is indicated by these curly brackets of the stochastic process, indicated with x sub t. And I say, okay, this is related to this first draw, if you like, from the sample space. So omega 1 is basically an element of the big omega, the sample space, and that generates a single draw from omega, generates a realization of the stochastic process. That would be a sequence of big T random variable, a sequence of realizations of big T random variables, which I represent in this graph here. Okay, I could also say, okay, but let's take another draw from omega. So maybe I'll have omega 2, which is also part of the big omega, and maybe I get something like that. Right? Another realization of the stochastic process, which may look like that. Again, a realization of a random vector, which I denote in the curly brackets xt, is a function of omega 2, like this. And maybe a third one, so we have omega 3, another draw from the sample space omega, and maybe this time I get something like that. Okay. The black one, same thing. It's a sequence of real numbers, which depend on this omega 3, and this is what we get. No? 3 draws from omega gives us the realizations of these three realizations of these big T random variables that we have here. Now, how can we conceive of these omegas, these small omegas? Well, they are, per construction, or as an idea, they are omega 1, omega 2, omega 3, and so forth, would be elementary events. They are part of the big omega, of the sample space. Sometimes these guys are referred to as singletons. What Hamilton calls these elementary events is essentially he calls them ensembles. You may also call them paths. Paths, basically paths of history, if you like. That would echo a bit Hayashi's idea of running history over and over again, and we see just one realization of the history, but in principle we could have observed other histories and like this. Maybe you like to think of these omegas as alternative histories or alternative worlds. And these alternative worlds would have yielded a different realization of the stochastic process. Maybe the blue one, maybe the red one, maybe the black one. Blue and the black or the red one. Right? These are possible realizations of the stochastic process, possible worlds that we could have observed. That's conceptually what we're trying to do here. Now, so these different colors that we see in the graph are basically a result of different draws from the sample space omega, sort of from the set of possible worlds, the histories that can be, that may be, if you like. 3 of them are depicted here. Now, the key issue here is the following. What is stated in Singleton's quote in the script, right? He basically say that what we do observe is essentially the single realization, which depends on the single draw omega, not in his example here, omega 0, that is taken from the big omega. So it's just one draw, and we observe realization of these random variables. That is, he says, associated with a single omega in the sample space. It's a single realization, one possible world. And now the question is, is that enough, right? What we like to have is we like to see different draws from big omega, that is different alternative histories to learn from the process, and this is stated here, right? In the second sentence. If you want to learn about the stochastic process, that is distribution of xt from this one realization, then we must, as we move along the series, xt of omega naught, this single realization, it must be the same thing as if we were observing realizations xt of omega for fixed t. But what we do is we let omega, the draws of omega, range over the big sample space, big omega. And that's the story. And that's the key issue behind ergodicity. We don't need to observe the process over and over again. It suffices to observe the process only once, but the information contained in a time series in this one realization of the process must be, when the time series gets long enough, the same as if we observed the process at one point in time over and over again. That is different draws from the sample space omega. And note that we're talking about a stationary process here. So the distribution of x1, x2, and x3 and so forth are assumed not to change. They're always the same distribution that we talk of here, right? So I could pick one xt out of the whole sequence and then observe this one xt over and over and over again. That's basically the idea. Or I observe the process in time, right? And information should be, if the information essentially that is contained in these observing the process over and over and over again at one point in time and observing the process in time at the same, then we call this process an ergodic process. And maybe it helps to provide an illustration of that idea to make the point even clearer. So again, here's a little draw, a graph. Here's maybe x. Here's time 1. Let me see. So here's one. Here's t. Here's t equal to 1. And now what we could do is we can run this process over and over again and observe different realizations of the process at this point in time 1. So I have different colors in my computer and I say maybe the first realization of x1 looks like that. And that realization depends on, I don't know, maybe omega 1, right? I take one draw from the sample space, and for x1 I get this thing. And then I get other realizations, maybe one here, maybe different color, one here, maybe different color, one here, another color, maybe one here, and so forth and so forth, and over and over and over again, I observe different realizations of x1. That's what we see here, right? So we have different realizations of x1 as a function of omega. So what Stingleton says basically, omega ranges over the big omega, over the sample space. We observe the process over and over again. And suppose we have enough observations, we can say, okay, why don't we draw something like a density over these observations? Maybe I get something in the end of the day, something like that. So here's a density, here's a distribution of x1. Density of x1 obtained from these different realizations, obtained from as omega ranges, small omega ranges over big omega. Okay, that's what we like to have, but alas, we can't have it. Now, the alternative that we have is the following thing: we have just one omega out there. Okay, one draw, one omega naught, say, one possible realization. And what we do is we basically observe the time series of that. So this is something that we observe, the time series thing, right? Maybe something like this and this and this. And maybe I'm jumping in the future here. Okay? And then it goes on like this. Okay? So we observe this realization of the process. What I could then do is maybe say, okay, take a look at these realizations that you have, and sort of take those realizations and plot them like we did for the colorful things, collect them and maybe construct a density of them over it, right? So here's my attempt. I say, okay, take this observation, have it here. Take this observation, have it here. Take this observation, have it here. Maybe take this observation, have it here. Maybe this one. Have it here, this one, have it here. So basically, see what I'm doing here? I'm taking all these time series observations that I get, and I'm plotting, I'm collecting them on this axis. Okay, and if I have enough of them, a long observation of the time series, long observation of the process, and if I would compute a density over these observations, then what should happen is that the distribution that I get from these time series observations, these non-colored points which I have here, these black dots which I have here, this distribution, the distribution that is constructed from these points, is the same distribution as the distribution that I get from these colorful points up there. That is observing the process over and over again, but not in time. So ergodicity basically means that the black density okay, there's this guy over here, this black density, and the blue density, this guy here, they become equivalent. If T gets large and the draws from omega get large too. Okay, and that's the basic notion here. We can learn from the time series, from observing the process in time. We get the same information as if we would run the process over and over again. And that's the notion of ergodicity that we're using here. And in this setup, as I draw it here, the process that I've drawn allegedly is a stationary process, so distribution doesn't change over time. Okay, that's one condition to talk about ergodicity in the first place. But that would be also a process that is ergodic. It suffices to observe the process over and over again, because see what happens if we move along the process, we basically collect the same information as if we were to observe this process over and over again at a certain point in time. And that's what is ergodicity. That's what ergodicity means. Okay. Now, let me give you one example where this is not the case, where ergodicity does not happen, or where ergodicity is not there. I'm talking about a process that I already had discussed in class. It's a stationary process, okay? And this stationary process is as follows. Okay, that would be an example of a stationary but not ergodic process. And here you shall see that the information that is provided by observing the process in time is not the same as what we would get if we observe the process over and over again at a certain point in time. Okay, and this process looks like that. X1 is coming from, is a draw from, say, a normal distribution with some mean mu and some variance sigma, and then X2 is X1, X3 is X2, which is the same as X1, and so forth, and X big T would then be the same as X big T minus 1, and this would be still the same as X1. Now this is a perfectly, is a nice stationary process, right? Its distribution doesn't change over time. This thing is perfectly correlated, right? The random variables are perfectly correlated, but that is not excluded by stationarity. Now let's take a look at the graph that we just draw in the previous example. Okay, and let's take a look at realizations of X1. Okay, so the colorful points which we have here are again realizations of X1. So I would get something like this, maybe a blue one, green one, something like that, maybe this guy, something like that. I'm running out of colors, but you get the idea, no? All these are different realizations of X1. Okay, X1 of omega, again, as omega small omega ranges over the big of the sample space big omega. And if we have that, and if we have enough of them, we could draw the density over these observations, and this thing would reveal that, okay, X1 actually is a normally distributed random variable with some mean mu and a sigma square variance. And we get this nice bell-shaped curve over them. Okay, that is what we could learn from observing the process over and over and over and over again, and see, oh yeah, these are draws from a normal distribution. But alas, this is not what we get from a time series, because the time series information it keeps omega fixed. So suppose we have this blue realization over there. What should happen is, now let me go to. Maybe go to T down here. This is the point T. So once the draw is the random variable is drawn, X1 is drawn, then the process stays fixed until until the process ends in some point in time. And now you can imagine, is in this case the information that is contained in the time series the same as it is contained in this repeated observation of the process? And the answer is clearly not. Right. So this process xt at, say, omega 1 is a process where we don't see any changes in the realization at all. We cannot learn anything from the time series observations of that process with respect to the distribution of x1. It's useless. Right? Same goes for this. Maybe the yellow representation down here would give us a fixed value, like this, straight line. From this realization, also nothing could be learned. The only chance to learn about the process is to observe it over and over again, but this is not possible. Point is, a time series observation does not help us at all to learn something about the process, albeit this is a perfectly stationary process. Okay. So we have at every point, every realization, we would have these straight lines, right? But they wouldn't help us. So here, black would be xt, say at omega 1, something like this, straight line, and down here the yellow realization, same thing, xt, maybe omega 3, no change, fixed. Once x1 is drawn, it's fixed. That would be an example of a stationary process, but one that is not ergodic. And this is hopefully after going through these illustrations, you will be able to grasp the idea that you find in this quote by Singleton, which is concerned with ergodicity. If we are to learn about the distribution of xt from one realization, then as we move along the series xt at a given omega, it must be the same as if you're observing realizations of xt of omega for fixed t, but let omega, small omega range over big omega. And that's the story behind this slide that we have in there. Okay, as I said in the slide, Singleton's definition invokes some concepts of measure theory. I've provided them in the first video, provided you with this explanation and the graphical illustration. So I hope you find that useful enough. It's mentioned on the slide that Singleton's definition of ergodicity is something that is harder to check. You find it easier to check a condition that is concerned with Hamilton's definition of ergodicity, and we'll come to that point in the lecture. I recognized one little error in the note of the first video, so I'd like you to correct that in your notes. So this arrow here should actually be an equal sign. So please correct that. Okay, now a little note on the use of these videos is I think it doesn't suffice that you just watch them and listen to me, but I think it's absolutely crucial that you actually write these things down, that you have your own hands-on experience in writing these formulas. Just watching formulas and also watching formulas emerge does not suffice. Furthermore, you're going to need these notes in the exam. Exam is an open book exam, so make sure that you have these notes like this also readily available in your notes that you carry along to your exam. It does not suffice to take pictures or take pictures in the lecture or of this thing. That is not enough. You really have to write things down, right? In the exam, you can't use the videos, you can't use your photos, you can only use handwritten stuff. So that's an important remark here. Okay, thank you very much for watching this video.